Today we will talk about lecture 4, chapter 2, data transmission. Okay. For data transmission, we will consider analog and digital data transmission. Okay. So what are data? Data are anything, okay, that can convey meaning. So it's, when you look at it, you know what it means. Okay, but you have to agree upon on how to interpret the data. Okay, what is a signal? Okay, signals and signaling. Okay, the signals are the electric or electromagnetic representation of data, and this one is the signal can frequently propagate through the medium or along the medium. So the signal is something that if you want to send through the air, it has to have some property, okay, so that it can go through the air. If you want to send it through the twisted pair, or you want to send it to coaxial cable or to fiber optics, okay, it has to have different property so that it can go physically go through along the medium. And what is transmission? Transmission is the communication of data by propagation and processing of signals. If you look at this figure, okay, this is the acoustic spectrum of speech and music. You can see that the x-axis is the frequency, okay, from 10 Hz to 100 kHz. The y-axis is the power ratio in decibels. The middle one here is a telephone channel. You can see that the telephone channel is between about 300 Hz to 4 kHz. The telephone channel is designed to pass the signal in this range, in this frequency range, because the speech is from about the speech for like that for human, okay. When we talk, okay, the frequency is from about 100 Hz to less than 10 kHz. Okay, so the telephone channel is designed over here. Let's look at another signal, the music signal. When you hear the music, okay, it's more beautiful, okay, than the speech. Okay, why is that? Because it has a larger frequency range, okay, from less than 100 Hz to about 20 kHz. You can see that the dashed line is the music spectrum, okay, and the solid line is the speech spectrum. For AM radio, okay, you can see that the upper limit for AM radio is a little bit more than the telephone channel. So it's covered most of the speech already, okay, of the speech frequency already. So when someone call and talk to the DJ, or when the DJ talk, okay, you hear almost the same as his voice or her voice. However, for the music, if you listen to the AM radio, the music in AM radio is not as beautiful as the music from the FM radio. Because the FM radio, you can see the vertical dash line, on the rightmost. Okay, this is the upper limit of FM radio. You can see that it's allowed larger range of the frequency. So in AM, you will not hear the frequency above the limit. Okay, so the some of the frequency will be lost. Even with the FM radio, some of the high frequency is cut off. So sometimes, you know, it's better to listen to the face-to-face, you know, like listen to the real musician, okay? If you listen in the radio, it will be different. The second topic we talked about channel capacity. The channel capacity is the rate at which data can be transmitted over a given communication path or channel, okay, under given conditions. So the channel capacity is like this. The channel capacity is like a pipe, okay? So if you have water coming through the pipe, okay, if it's water, okay. The pipe that has large diameter and the pipe that have smaller diameter, okay. You can see that the water can pass through this more than this one, okay, because this one diameter is smaller. This is the same as the channel capacity when you send the data. If you have the high channel capacity, okay, it's the same as you have a large diameter, okay, to allow the data to flow. But if you have low channel capacity, then you have a small diameter, okay, of the pipe, of the channel that the data can go through. Okay, so what are the key conditions, okay, to determine what is the, the size of the channel capacity, okay? The key conditions are the bandwidth and noise, okay? For the noise, we can think of it in terms of signal to noise ratio, okay? Because if the signal is much higher than the noise, it will be okay. You see that the S over N, signal power over noise power in dB unit is equal to 10 times log base 10 of signal power in watt, okay? Or in watt over noise power in watt. So the signal to noise power in dB, okay? So the signal to noise power, if there is a ratio, there will be no unit, okay? But if it's the dB unit, it will be 10 times log base 10 of the signal to power to noise power. Now, Mr. Shannon, okay, proved that maximum channel capacity for the channel that has only the additive Gaussian noise, okay, the base channel, base possible channel is C equal to B times log base 2 of 1 over S over N. S over N, this one has no unit, okay? This is the ratio. In ratio, it's not the dB, okay? And the unit is bits per second. So B is the bandwidth of the channel in hertz, and S and N, as I said, is in ratio, okay, and not dB. Shannon proved that all data rates below maximum channel capacity are achievable, okay? He proved the channel capacity, channel coding theorem. If appropriate codes are used, okay, so you can get maximum channel capacity, okay, if you use suitable codes. However, his theorem didn't tell you, okay, a way to find the codes. So there are a lot of researchers, okay, who try to find this suitable code, okay, that can give you the maximum channel capacity. And so there is a field about error correcting code, okay, which is another class 01205-525, which is channel coding theorem. But anyway, none of these error correcting code that have been found satisfy the theorem. Some are very close, okay. But the proof of this theorem requires knowledge in information theory. So this is beyond the scope of this course. But I mention it here because this class is a graduate level class in เกษตรศาสตร์ University. It's called channel coding theory, which I'm also teaching. So if you are interested. Okay, now let's look at the question. What will happen when the bandwidth go to infinity? Okay, to calculate the channel capacity as B go to infinity, we have to look at some relationships. Okay, about the log, okay, function. Okay, you can see that for the first one, natural log of 1 plus x is approximately x. Okay. And 2, log base 2 of 1 plus x is approximately x times log base 2 of e. And 3, limit as b go to infinity of 1 plus a over b, and the total to the B, okay, as you can see in the slide here, equal to e to the a. So now if you want to calculate the channel capacity as b go to infinity, from the channel capacity, C equal to b log base 2 of 1 plus s over n. Let's look at this. C equal to b log base 2 of 1 over s over n. 1 plus s over n, okay, bit per second. So this one, n is the noise power. Noise power is equal to n naught multiplied by b. This is the noise power density. B is the bandwidth, okay? So we can rewrite this as b times log base 2 of 1 over s, 1 plus s over n naught b bit per second, okay? And then we use this one. We use this the second relationship here, we use log base 2 of 1 over x, approximately x log base 2 of e. So if I let x here equal to this, okay? So this is my x, okay? Therefore, C will equal to b, okay? And this one is this, okay? So this one will be s over n naught b log base 2 of e. Can you see? Because this one is x, okay? And this is x log base 2 of e. So this is x log base 2 of e. And then b cancel out. C equal to s over n naught log base 2 of e. This is when b equal go to infinity, okay? When b is increased and go to infinity. Okay, so we can see that as b go to infinity, the channel capacity, the bandwidth go to infinity, the channel capacity go to s over n naught of log base 2 of e. Okay, now, why would I show you this? Because in this formula, in this channel capacity formula, you can see that there is two main parameters, the bandwidth and the signal to noise ratio. You can see that if you increase the signal power, okay, your channel capacity will always increase, but it will increase less than when you increase bandwidth, because it is inside the log base 2. Okay? So when you increase the channel capacity, the signal to noise ratio, even though it's increased, the channel capacity always increase, it will increase less than when you increase the bandwidth, because the bandwidth is outside. However, so it looks like if you increase the bandwidth to infinity, you can get the channel capacity go to infinity too, which is not the case here, okay? Since the bandwidth is also inside of the noise power, that's why there's a limit on the channel capacity even though you have unlimited bandwidth. So you cannot get higher channel capacity by having more and more bandwidth, okay? It will saturate at some point. So this one, the subscript over there is kind of wrong, but because it's printed. Anyway, so C equal to log base 2 of 1 plus S over N0B, okay? That's the dash line, but the blue line is the one that it will approach. Okay, so sorry. So sorry, the blue line is the channel capacity, and the dash black line is the limit. Okay, it's S over N naught of log base 2 of E. The blue line is the channel capacity equal to B log base 2 of 1 plus S over N naught B. The next topic is gain and attenuation in dB. I think this one A lot of people already know, okay, from the first and second year that you have studied. Anyway, if you have a system, okay, and you have power in P1 and power out P sub 2, okay, the attenuation means that the power out is less than power in because you put something in and then you get less out, it's become attenuation, okay. So attenuation is, the formula is A in dB 10 log base 10 of log base 10, okay, P1 over P2. P1 over P2 because P1 is more than P2 because this is attenuation. You put in something and you get less. Attenuation is a positive number. Okay, so P1 over P2 here. If you think in terms of voltage, okay, it's going to be 20 log, okay, of base 10 of V1 over V2. But if you calculate the gain is different. The output is more than the input. You have a gain, okay? So gain G, the gain equal in dB equal to 10 log base 10 of P2 over P1. So you can see that this is different. So if you have a gain of equal to 3 dB, it means that you have attenuation of minus 3 dB. If you have attenuation of plus 5 dB, then gain is minus 5 dB. Okay. So in terms of voltage, it's similar, okay? Gain is equal to 20 log base 10 of V2 over V1. It's the voltage, okay? Next, we'll talk about transmission impairment, okay? Because of the transmission impairment, it is impossible to get the exact pulse shift at the receiver. You send something through the channel and something, affect your signal. So whatever you receive will not be the same as what you transmit, okay? It will never be the same because we always have noise and we may have some distortion, okay? And we can have some attenuation. So if you look at the bowl, okay, here, our goal is to be able to correctly decide, okay? We want to be able to decide whether 0 or 1 was sent. This is for digital communication, okay? If you send the shape, this shape represents 0, another shape represents 1, okay? You just want to know whether 1 or 0 was sent. You don't have to receive the perfect pulse shape, okay? As long as you know what it is. Now let's look at an example. If you send something, if you say that, okay, this is my 1, this is my 0. 0 is sending nothing, okay? Then you receive something like this. Okay, what is it? What should it be? It's not the same as this one, but what should it be? Should it be 1 or 0, okay? Most of you will say it's a 1, okay? And most of the receiver will say it's a 1, okay? Because it is similar to this one more than this one. So you don't have to know, you don't have to get the exact, the correct, perfect pulse shape here. If you receive something like this, okay, what is it? Okay, most of the receiver will say it's 0, okay, which will be correct because when you get something like this, it's similar to this one, okay? If it's not very low probability that this one gonna be this, okay? Very low probability. It's possible, but it has a much lower probability to be 1 than to be 0, okay? The main transmission impairments are first, attenuation, second, distortion, and third, noise. What is attenuation? Attenuation is that the strength of the signal is reduced when it is sent over any transmission medium. So when you send something over the line, if at first you send 2 watts, okay? When you send over the line, okay, you get less than 2 watts, definitely, okay? Whatever medium that you use, if you just send it in the air or in the coaxial cable, okay, you will get less power out. This is because there's attenuation. If you want to use, if you want to increase the received signal strength because it's not enough to detect, for example, okay, you want to get higher signal receive signal strength, you can use amplifier for analog signal. So the amplifier will boost, okay, the analog signal to be higher amplitude, okay. And for the digital signal, you can use repeater. Repeater will regenerate the signal, okay. If you look at this, for analog signal, okay, if it's like this, you go to the amplifier, okay. You got something like this, okay. It's the same shape, but it's bigger, okay. Maybe not very nice. Let's use this, okay. Let's say this is amplifier. Okay, so you get suppose it's the same, okay. So you get a higher amplitude. But if it's a repeater, what the repeater will do is this. When you receive something like this, okay, the repeater will decide, okay, what is this? It should be 1010. It should be 1010, okay? So it will reconstruct, okay, a nice pulse shape like this, okay. So the repeater will make a decision on what the bit sequence should be for this signal waveform, okay, and then it will reconstruct the signal, okay. It's a clean shape signal, okay. But this one is just same shape but higher amplitude, okay. And attenuation is increased, okay. It increased with frequency. So at higher frequency, you get higher attenuation. So different frequencies have different attenuation, and that is one of the problems. If you look at the attenuation curve, okay, for a voice channel, you can see that the x-axis is the frequency in hertz. The y-axis is the attenuation in decibel, okay. Without the equalization, the solid line without the equalization, you see that when the frequency increase, the attenuation value increase too. But if you want to make it less, you know, you want it to be more stable, okay, like similar for all frequency, you can use equalizer, and this is the dashed line is after the equalizer, you will get the attenuation that is better than the one without the equalizer. It's more stable, okay, like similar for all frequency, okay, even though it's not all of them, but it's better than the solid line. Now let's look at the distortion, okay. For a linear time invariant system, no distortion means that the two following criteria are met. What are them? The first one is that the amplitude response is flat, which means that the amplitude response of HF is the amplitude response of the system, okay, equal to constant, okay, so it's flat or equal to constant. The second criteria is that the phase response is a linear function of frequency, okay, which means that the phase is equal to minus 2 pi f times t sub d, okay, where t sub d is the time delay. Phase equal to minus 2 pi f of t sub d. This is a time delay, okay. Now, why should we use this criteria, okay? Why should we use this criteria? Suppose the transmitter sends a signal, okay, xt, and the receiver receives the signal yt. If the yt is in the form yt equal to a constant, okay, a constant k equal to times function x of t minus td, where td are constant, the time delay, you will see that this transmission is distortionless. This is the best that we can hope, okay. This is the best that we can hope. Why? Okay. Because when you send something, okay, there's always a time delay. If the time delay is equal to 0, mean that they use no time to send, which means that whatever you are sending now, the receiver receives at the same time. Okay, if TD equal to 0, not possible. Okay, because there must be delay for the signal to travel from you to the destination, even though the delay may be picosecond, nanosecond, but cannot be 0. And K is, as I said before, that when you send through the transmission medium, you will have attenuation, right? So what you receive is not doesn't have the same amplitude as what you have transmit. Okay, it have lower amplitude, lower power. So we have if it's lower in terms of like a constant, which means that the signal that you send, let's say you send this signal and you receive this signal. Okay, this is okay. Okay, this one is okay because you receive the same shape but smaller amplitude due to the attenuation. Okay, so this one K is the base that you can hope it cannot be 1. If it's 1, it means that what you send is the same as what you receive. Okay, the same amplitude. Okay, you can maybe put it if it have to be a 1, you can put it like an amplifier at the end or something, but anyway, K has to be constant and the TD cannot be 0. Okay. Also, TD cannot be negative because if TD is negative, it means that it's non-causal. The receiver receive it before you transmit it. Okay. So TD must be more than 0 always. Okay. So this is the best that you can hope for, but usually you will not get that. Okay. However, we should have a benchmark of, okay, this is a standard that we hope to have. If you take the Fourier transform of equation 2.7 of this equation that I just talked about, we have the Fourier transform of yt equal to y, capital YF, okay, equal to k is the same. And Fourier transform of x of function f of t minus td is that there is delay in time, mean that there is a phase delay, okay, phase in frequency. So it's going to be k times e to the minus j omega t sub d times x sub f, okay. So this is from the Fourier transform pair, okay, that you should have learned from signal system class. Now, if you compare this formula to another formula here, so YF equal to HF multiplied by XF, okay. So what will happen? One equation is that YF equal to K times e to the minus j omega td multiplied by xf. Another equation is the normal equation, okay, is the equation, a general equation, okay, yf equal to hf multiplied by xf, okay. This is the general equation when you send something, okay, xf into the system, hf you get yf. Okay, so from these two equations, what can you see? You can see that xf is the same, right? So hf must be equal to this one. Hf must be equal to this one. Okay, so you know that if it's gonna be transmission, gonna be distortion rate, hf has to be equal to k, constant k times e to the minus j omega t sub d. Okay, so this is our criteria. Okay, or we can write this as minus j and phase. Okay. Okay, so you can see that to have the hf equal to k multiplied by e minus e to the minus j omega td, it means that the phase has to be linear. okay, with omega. Okay, TD has to be constant. Otherwise, you cannot, you will not meet the second criteria. Okay, now let's look at, this is a very simple example, okay? Just to show you that if you have a frequency response like this, the amplitude response is the upper graph, okay, and the phase response is the lower graph, okay? What you want is that you want the amplitude response to be constant. And it's kind of sort of constant from 20 to 50 hertz, okay? You can put like megahertz or kilohertz, okay, at the unit, okay? But let's say 20 to 50 megahertz, okay? And the phase response is linear from 0 to 30 megahertz. So what happened is that where is the range that we can use, okay? What the range that we can use for distortionless transmission is between 20 to 30 megahertz because 20 to 30 is amplitude of the system equal to constant, okay? It doesn't have to be 1, okay? It just have to be constant. And the phase response is linear with the frequency. So it's going to be a straight line with negative slope, okay? As I say, this one, okay, you can put kilohertz or megahertz as a unit here. That's, okay, should be K there, or you can change this to megahertz and this one to megahertz. Linear and nonlinear distortion, okay? Anyway, this is not a real system, okay? This is just an example to show you the, to follow the formula where should you use to get distortionless transmission, okay? Now let's look at the linear and nonlinear distortion, okay? The linear distortion can be compensated by using an equalizer. As I showed you before in the graph that when you have an equalizer, okay, you will get a better response, better kind of the flat attenuation, okay, flatter attenuation. Now, if you look at this system, if you have the original system HF, okay, and if you put an equalizer next to the system, okay, so you have H sub E, and this is the frequency response for the equalizer, okay. The new frequency response of the system, okay, of the new system will be H prime F, which is the multiplication of HF and H sub EF. So you get something like this. So how to get, how to find an equalizer, okay? We want equalizer to be a constant, right? You want it to be a constant. So you want, if you change, okay, you take the HF to divide out of H prime F, you get this formula. And you can see that if, let's look at the figure, okay? If HF is like this, curve down like this, okay? And when you found the H sub EF, okay, you found that it have to curve up, okay, so that it can cancel each other. So when you multiply them together, you get the amplitude response of H prime F, okay, is a constant. So this is a very simple example, okay, to just give you the sense of how to find the equalizer. Now let's look at another transmission impairment, okay. We have talked about the distortion, we have talked about the attenuation, okay. The last one is noise. Noise, there are many noise in the channel, okay. The first one is thermal noise. Thermal is like temperature, okay. So the thermal noise is occur, okay, for all temperature above the 0 degree Kelvin. So if you have the absolute 0, no 0 degree Kelvin, then you have no thermal noise. But since we cannot go to absolute 0, okay, we always have thermal noise. So this is a noise that increases with frequency, with temperature. Next is the intermodulation noise, and we talked about crosstalk and impulse noise. Now let's look at the thermal noise first. Tomo noise may look like this, okay? Usually it is, it have a distribution, we can represent it with Gaussian, okay? With Gaussian white noise, additive white Gaussian noise, okay? So you just have like the value going to be follow like the Gaussian curve, okay, PDF. This is due to the random motion of electrons, okay? The thermal noise due to random motion of electrons. When electrons move around, okay, and collide together, okay, they give heat out, okay? Thermal noise is a type of white noise, okay? And white noise means that there is, this noise has all frequency, okay? And it have the same value for all frequency, which means that it's constant or flat all over all frequencies. Because if you think about the prism, okay, when all the light, all the color combining, you got white, okay? So all the frequencies have the same spectrum value, okay, for this noise. So it is called white noise. We can look at this. We don't have it here. So white noise will be like this. We will have the PDF, PSD, power spectral density. Of white noise, okay, this is frequency, okay, so it have its constant over all frequency, okay, so it have value like this. So we call this noise that have power spectral density or PSD or the spectrum equal for all frequency, a white noise. Now, white noise is the worst kind of noise because it cannot eliminate it, because it's uniformly distributed. It's the same over all frequencies, so you cannot avoid it. With whatever frequency that you are transmitting, you always get affected by the white noise, okay, or thermal noise. And we use the power spectral density or PSD to measure how strong the noise is, okay, at different frequency. Anyway, this one is easy to calculate, okay. It's the worst noise in terms of that we cannot avoid it. We cannot eliminate it, but it's good in terms of calculation, okay? It's very easy to calculate. Okay, now what is PSD? PSD describes the power content of a signal, okay, as a function of frequency. So it knows how much power is presented given various frequency bands, okay? So the power spectral density of white noise is constant and equal to N0 over 2, okay, where N0 equal to K times T with the unit of watts per hertz. What is K here? K here is Boltzmann constant, which is 1.3803 times 10 to the minus 23 joules per Kelvin. So this is Boltzmann constant. You can just plug this in, this number. And T here is a temperature in degree Kelvin. So if you have Celsius, okay, if you are like 30 degrees Celsius, then you have to add 273 Celsius, okay? To get the Kelvin, 273 plus 30 gonna be 303 Kelvin, okay? And the higher the temperature, the higher the noise spectral density, right? From the formula here. So this one doesn't have N0 will be 0 when T equal to 0, which is absolute 0 or 0 Kelvin. When you look at this, you can see that, okay, this is if you want to find the noise spectrum, because when you send signal, you will send in some bandwidth, okay? You are not sending for all bandwidth, all frequency. You will send from, for example, from 1 megahertz to 2 megahertz, okay? So you have a bandwidth of 1 megahertz from F1 to F2, okay? As you know that when you write the frequency domain, okay, usually you write also the negative part, okay, so that it will be easy for understanding, okay, which is not the real frequency. Anyway, it's good for it's easy for calculation. And for this case, the power, as you know that N0 is the power spectral density, right? For the noise power is equal to the density times the frequency, okay? So you know that N0 is the noise density, and N equal to noise power. So the noise power equal to the density multiplied by the bandwidth. This one is watt per hertz. This one is hertz. So when you multiply, you get watt. Okay. So you will get N equal to N0 over 2 is the height multiplied by the bandwidth. The bandwidth is 2 times F2 minus F1. If you look at the formula here, you can see that N0 over 2 is N0 over 2 is the height of the spectrum. Okay, multiplied by you have two boxes here. Okay, on the negative side and on the positive side. So 2 times of the F2 minus F1. Okay, and you get N0 is K times T, right? And F2 minus F1 is B, so you get KTB, okay? You know KTB is like Kung Thai banking, okay? So it's very easy to remember. Anyway, so noise power is KTB. K is the Boltzmann constant, T is the bandwidth in Kelvin, the temperature in Kelvin, and B is the bandwidth in Hertz. Okay? For enthusiastic students, okay, if you're interested, do you know there are also color noise, such as a pink noise, a red noise, a brown noise, and gray noise? And you can find this information in the Wikipedia, okay, color of noise. You can also listen to them, okay, what is sound like, what does white noise sound like, what the color noise, okay, pink noise, red noise, brown noise, gray noise sound like, okay? You can look it up. Okay, next is the intermodulation. Intermodulation noise, you can see that you have, okay, this is I got from the Wikipedia too, okay? When signal at different frequencies, okay, share the same transmission medium. So you send in the same transmission medium or the same cable, okay, you send signal with 2 different frequencies, okay? What happens is that you can get intermodulation noise, okay? Because from this figure, okay, you send the signal at 270 megahertz and 275 megahertz, okay? These are the last spike. These are the signal you actually want to send the last peak, the 2 last peak here, 270 megahertz, 275 megahertz. And you will get intermodulation noise, okay, at the 280 and 265, okay? So it can be, so you can see that the small spike, okay, that show up, okay? You can see the small spike at the both sides, okay, of this. Okay, so if you want to send another signal at 280 megahertz, it will be interfered by this small spike here. Okay, if you want to send another one at 265, it also interfere by this small spike here. So you have to be careful that if you send more than one signal in the same cable, more than one frequency, then this can happen. This noise occurs due to the nonlinearity in the transmitter, receiver, or the transmission system. So if in any if there is any nonlinearity, okay, in the system, okay, they can have this intermodulation noise. Now let's look at impulse noise, okay? Impulse noise, okay, this is from my graduate student because he generated this and but I'm not sure how to where it's published, okay, so how to reference him. Anyway, there's noise spike of short duration, okay, with high amplitude. So this one you have spike, okay, high spike, okay, occasionally. So usually you have like background noise, okay, the small amplitude noise, and then occasionally you have large spike noise, okay. These are unpredictable, okay, and the primary source of error in digital data communications. When you have the impulse noise, it's like in a power line communication, okay. Let me talk a little bit. When you transmit through the power line, PLC, okay, has background noise and impulse noise, okay. And the impulse noise can come from when you turn on, turn off your, you turn on, turn off your electric device, okay. So they have kind of a spike from the high power at very short time, okay. So this one is a problem in PLC. And so when you send the digital signal through the PLC, you have to try to overcome this problem, okay. So you have something like, okay, you have to solve like how to do it with this, okay. Actually, in my research, I have some like coding method, okay, the error correcting code to correct this. Okay, now I said that the digital signal, for digital signal, okay, for digital signal, the impulse noise, okay, is a main effect of errors, okay. Because if you look at the case of analog voice, if you send analog voice, if I'm saying and then there's some noise interfere, okay, with my speech, okay, very short time and very high power, okay, you can understand me because the signal will be something like this. You will get some signal something like this. You have high, this is analog, right? And you will have some spike. Let's say you have some spike over here, very short, or some spike over here, okay? When you listen, you say beep or something, and then you can still understand what I'm saying, right? But if it's digital, okay, what happens is that you send very fast, right? Very fast data rate, okay? So in, let's say if you send with 5 megabit per second, 5 megabit per second, it means that 5 million, okay, bit per second, okay. So what happens if there's a spike for like, let's say 1 millisecond, okay? 1 millisecond means 10 to the minus 3 seconds, okay. If you have a spike of 1 millisecond, you will get 5,000, okay, 5 million multiplied by 10 to the minus 3. So you have error, burst error of 5,000 bit already, okay. And if you want to send with a higher data rate, okay, you will get longer burst error, okay. So you will have a problem like that, okay. So there are many problems with the noise, and we have to try to overcome them. Even though there are always noise in the system, we have to design the receiver so that we can make a correct decision of what is transmitting, okay. And that's all for this tape. And for the next tape, we'll talk about chapter 3.